Namaste. Can you hear me?
Yeah, loud and clear.
Yeah, great. I can hear you too. Namaste.
Nam-
Yeah.
Namaste.
Bhaskar, hello and welcome to this very special occasion whereby we are all assembled here to commemorate the Punyatithi of the legendary Ganitagya, the legendary mathematician of Bharat, Srinivas Ramanujan. At a very young age of 32, he left his material body to his heavenly abode. But the meticulous works what Ramanujanji brought in the form of mathematics to the whole world is something unprecedented. And perhaps after, I would say, at this young age, Swami Ramatirtha, at that very Vedantic young age, I think Srinivas Ramanujan.
I won't share a present. It's a short session, so I won't do a present.
Yeah, just sorry, I'm just, yes. So, Ramatirtha. Uh, and so this is quite a solemn occasion for that matter. And as you can see on the backdrop, the kind of work what Ramanujan created in that three odd decades of the whole life, of which obviously the childhood, early childhood, and all his mathematical genius, we are all seeing it across. And this uh, I'm just, yeah. So that is truly marvelous out here. And today we are all assembled here to commemorate that mathematical genius, the man who knew infinity. And the whole mathematical world is still in enigma about the work which he produced. The Ramanujan diaries are still to be decoded by some of the best mathematical minds of the world. His entire works pertaining to infinite series for pi, Mach theta function, Ramanujan number, hypergeometric series, the Riemann series, the theory of divergent series, the functional equations of the zeta function, theta function, circle methods, game theory, the elliptical integrals. You can go on and on and on. And one of the most important aspect of Srinivas Ramanujan was his very humble admission. He used to bow down to his Kuladevi and name her every time whenever he was asked upon that where he has got those sparks, those mathematical imaginations. And one of the quotes of Ramanujan was that an equation means nothing to me unless it expresses a thought of God. So, always the mathematical, mysterious, mystic, or metaphysical mind, as we can say, Ramanujan. And today we have got the distinct privilege of yet another very young mathematical, I would say, a genius in his own way, Dr. Bhaskar Kamble, who would be illumining us, who would be talking, who would be giving us some ideas as to how to resuscitate the legacy of Srinivas Ramanujan. And Dr. Kamble is an eminent scholar, and I would just like to read out a brief of his, I would say, illustrious personality. You will all get to know him more from his talk. He's an author, he's a theoretical physicist and a data scientist, and he obtained his PhD, the doctoral degree in theoretical condensed matter physics in the year 2010 from the Bharatiya Pradyogiki Sansthan Kanpur, and therefore he worked as a researcher for several years at various German and South Korean universities, some of the top-notch research institutions, and specializing in the fields of unconventional superconductivity, quantum phase transitions, and many particle physics. And currently, he works as a data scientist in Berlin, where he lives with his family. So, a short, sweet introduction, and without any further ado, I would invite Dr. Kamble to commemorate this very solemn occasion of the Punyatithi of Srinivas Ramanujan, and how, as a nation, as an aspiring nation, we can resuscitate the legacy of the mathematical legend. Over to you, Dr. Kamble.
Yeah, thanks a lot, Raghavji. I would need to share my screen, and it is not possible.
Sure, sure. I'm just doing it. Yeah, I'm just. You can do it now. Yeah, please.
Okay. Um, and I will just, I'm wondering to share the screen or the desktop. Okay, can you just tell me if it is visible,
Yeah,
if
yeah.
my,
Perfectly
oh,
okay. Perfectly okay. Yeah.
all right, then I will go to full screen. Uh, yeah, is it all fine?
Yeah.
Okay. So, do you see this table with Aryabhata's sine table?
Yeah. 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 Very much.
And is this equation, this red box, the whole equation inside this visible?
Yes. Yes. Yes.
Okay, I'm just asking because in my case, the Zoom window is covering that. That's why I don't want, I hope that it is fine for you also,
Yeah.
everyone else. Is it? Okay, great. So, yeah. So, Raghavji, many, many thanks for this kind introduction and for this, great honor for being able to give this talk on the occasion of Srinivasa Ramanujan's death anniversary. I am deeply humbled that you put me in the same category as Ramanujan. It's a very yeah. I would not really consider myself in any leagues with Ramanujan. He's yeah extra, yeah. I don't know what to say. Genius, super genius. Uh, yeah, exactly. So in this talk, I thought, I will speak about some of the aspects of the tradition of the mathematical tradition from which Ramanujan comes, the Hindu civilization, and before I begin, I just a few words I would like to just mention here that uh, as you all know, as you have also already said, that Ramanujan was a mathematical genius. But what we often forget, because of this extreme focus on Ramanujan's genius, we forget that he comes from a tradition which already had a rich civil tradition of mathematics, rich heritage of mathematics. And this is something which is like an unfortunate effect, and we sort of also started respecting him only when he was um, acknowledged by the West. So this is something which is kind of unfortunate. And the fact remains is that his thinking was closely aligned with the Hindu philosophical thought, Hindu spiritual traditions, thinking processes. And for example, you said that you mentioned that he's often described as the man who knew infinity. But we may remember that this idea of infinity, one of the first ideas, maybe the first idea, was enunciated by Bhaskara too with his Khahara in the I think in the Lilavati Khahara. And where he also makes his comparison with Lord Vishnu, this the whole idea of Khahara. So these are some very important things we need to keep in mind, that we don't forget the roots from which he came, the civilizational roots. I got interested in the history of Hindu mathematics since around 2014, and I was researching on this topic in my free time, and finally it resulted in the publication of this book, The Imperishable Seed: How Hindu Mathematics Changed the World and Why This History Was Erased. And yeah, I will just there's in which I talk about the contributions of Hindu mathematicians and the transmission and the close connection of Hindu mathematics with Hindu spiritual ideas, philosophical ideas. And also, I devote the last section of the book to understanding why this is absent from mainstream historical narratives. One important thing I just want to mention before I proceed further, because I may be, accused of being communal or something, or narrow-minded or parochial by using the word Hindu. Why should I use the word Hindu and not Indian? So I would like to make it clear here that the ideas of Hindu mathematics are actually closely aligned with those of the Hindu civilization, the Hindu philosophical ideas. So, India is a geographical and a political entity, and of course, there are many other religions, Islam, Christianity in India. But obviously, these sections don't identify with the civilizational aspect of the Hindu civilization. So, it becomes important to make this distinction and not use the word Indian, which is very misleading and yeah, generic, and not generic, but very misleading. So that's why I think Hindu is the appropriate term, and it also includes other dharmic streams of thought like Jain. There have been many Jain mathematicians also, Hemachandra Halayuda, who did great work in prosody and mathematics, Mahavira from Mysore from the 9th century. So I include all of them within this term Hindu because they have certain civilizational similarities in all their things. So the Hindu mathematical tradition has made a very groundbreaking contributions in so many areas of mathematics, foundational areas of mathematics, like numbers and arithmetic. We all know what the situation was with the Roman number system, with the earlier number systems, Babylonian number system, how difficult it was to make these calculations. Then the subject of algebra, which is in fact a generalization of arithmetic, as I have discussed in my book. In fact, the ideas of algebra follow naturally from the ideas of arithmetic as the Hindu civilization developed them. The subjects of combinatorics, linguistics, prosody. So combinatorics, linguistics, prosody, they have a very algorithmic approach. And the word algorithm itself, is attributed to Al-Khwarizmi, but actually it's a very ancient technique coming from the Hindu civilization, from Pingala, Panini, whose ideas influenced even, computer science 2 millennia later. Then the subjects of trigonometry and calculus, almost the whole of trigonometry we study in school, it comes from India. All the major results we read in school. The ideas of calculus has a long tradition from Aryabhatta till the Kerala mathematicians. So in a nutshell, most of the school mathematics and a bit of university mathematics as well. In this talk, I decided to focus on two aspects. That is, one was the calculus in Aryabhata's mathematics, and the second one was some aspects of the Sulba Sutras. So I thought, that this audience consists of, as I was told, that this audience consists of some mathematics instructors, and so I thought I could, in fact, make it a little bit more technical than I usually do, and it's a little bit different kind of a talk than I usually give on this topic, and it includes a lot of new material which I researched on after the publication of the book, which I'm very excited about to also to share about with. Yeah.
I'm sorry. I'm sorry.
Yeah.
Please carry on.
So the first part, as I mentioned, was the calculus in Aryabhata's mathematics. The calculus in Aryabhata's mathematics is closely connected to trigonometry, in which, and as mentioned, the whole field of trigonometry arose in the Hindu civilization. They had their own terminology. The modern sign we used to be called the ardhajya, and later on it came to be called as jya, and cosine was to be known as cotijya, and this all follows from this bow and arrow kind of a picture which you see here, because because the word jya means string and so on. So this terminology follows that sort of a picture. And jya, cotijya, they traveled to Arab world and to Europe, and they became the modern sine and cosine, which I will not talk today. But they also made use of this trigonometric circle, which we use as today as the unit circle. But in Hindu mathematics, they would take the size of the length of the circumference as 21,600. So that would be 360 times 60. So they would divide this circumference into 360 times 60, what we understand as minutes today, degrees and minutes. So many minutes in number, so 21,600 minutes. So, and the radius of the circle they would take to be 3,438. That would lead you to a value of pi, which is about 3.1416 approximately. And later on, and if they wanted to have more and more accurate values of pi, they would just adjust the value of this radius accordingly. Instead of 3,438, they would have the corresponding higher accurate values. So this is what I just mentioned here. So with this background, we can look at some of the works of Aryabhatta. So Aryabhatta was sometime in the 5th century CE he lived, and he's known for his works, most famous for his work Aryabhatiya. And also he was author of some other works which are lost to us now. Aryabhatiya is a very short piece of work with very like sutras, almost you can say, very short statements of results. And there he gives one section he devotes to the values of the sine function. So he gives a value of the sine tables, the value of the sines for 24 different angles in the first quadrant. So if you divide 90 by 24, you get about 3.75 degrees. So in multiples of 3.75 degrees, he gives the value of sines. But it's very interesting that he does not he gives the value of sines as a like numbers values, but he also gives the a method for finding out in terms of second order sign differences. So second order sign differences, and the verse is given in this here in on this slide. So I'm not going to read it out right now, but we can just try to understand what the second order difference means. So from this table, so this I is it goes from 0 to 24. So there were 24 angles right here we saw. And then this alpha is 3.75 degrees, this smallest angle. So it goes in multiples of alpha from 0 to 24. And the first order difference would be simply the difference of the signs between this angle alpha and the previous angle alpha. So for example, if you look at I is equal to 4, you have a sine of 4 alpha minus sine of 3 alpha. So the difference of the signs between sine function between this angle and this angle. Similarly, the first order sine difference would be this 3 sine 3 alpha minus sine 2 alpha. So this would be denoted by delta. This is the first order sine difference, and the second order sine difference would be delta 2 minus delta 1. So this difference minus this difference. So it's a very abstract kind of way of thinking. It's a very sophisticated way of thinking along these terms. So he gives the procedure for using this method to obtain the values of the sine functions, and what is really interesting in this is that this verse there is a certain ambiguity, so it can be interpreted in two different ways. So this is one of the interpretations along which it can be understood. And there is also another way in which understood where I have given this. This is the second interpretation. So I will just look at the first interpretation. So if you look at here, yeah, so delta 1 minus delta 2, it was, where was this? Yeah, so delta 1 minus delta 2, if you do the calculation, it comes out to be approximately 0.963. So that is, he takes to be approximately equal to 1. And if you just make this substitution, delta 2 is equal to then this, and delta 1 turns out to be equal to r sine alpha. So because r sine 0 is 0, so delta 1 turns out to be r sine alpha, and you get this sort of a thing. So if you can, this is how you can understand the first sentence. The first r sine, that is r sine alpha divided by itself. That means r sine alpha divided by r sine alpha, which is of course 1. And then diminished by the quotient. So this is the quotient, and this is the first r sine. So this minus the quotient will give you the second difference. So this is the sentence which this expression is embodying. And we see that this follows from this. If you put 0.963 approximately equal to 1, so this follows from this. For computing any other difference, the sum of all the preceding differences is divided by the first r sine, and the quotient is subtracted from the preceding difference. So if you want, for example, delta I plus 1, you first take the preceding difference, that is delta I. If you bring delta I here, you have delta I plus 1 is equal to delta I minus r sine I alpha divided by r sine alpha. So this is divided by the first r sine, and what is the quotient? The sum, numerator is the sum of all the preceding differences. This is r sine I alpha. It is the sum of all preceding differences, because you can just see it by adding delta summation of delta I. You have this telescopic sum where each term cancels in pairs, and you are left with the last term and the first term, and that you are left with r sine I alpha. So this is what is given here. Now, very interesting part is that in discrete mathematics, the second order sign difference is analogous to the second order derivative in calculus, continuous calculus. And here we see a very interesting fact that the second order sign difference is proportional itself to sine of I alpha. And this is the discrete analog of the fact that the second order derivative of the sine is proportional to the sine itself. So this is like in a discrete analog of the differential calculus in Aryabhata's this result. Now there is a marvelous sleight of hand that this verse can be interpreted in a slightly different way, as has been commented upon by Parameshwara and Nilakantha in the 14th, 15th centuries. And here is this interpretation. So according to this interpretation, you have the first sentence remains the same. The first r sine divided by itself gives the second R sign difference. This we saw, this remains the same. This is this formula here. It's what given. And the same first R sign diminished by the quotients obtained by dividing each of the preceding R signs by the first R sign gives the remaining R sign differences. So actually you have to take a sum of the preceding R signs. So R sin alpha, R sin 2 alpha plus R sin I alpha. And then you have to divide this by the first R sign here. And this gives the remaining R sign differences, so delta I plus 1. So this you can see that actually, like, I know I'm not expressing it very well, but basically this formula is what embodies this verse here. And you can see here that this is actually an discrete analog of the so-called fundamental theorem of calculus. Because you just what is going on, this is here, this is the the sum of these differences is like an integral. And in each of these differences of the second order sign differences, we saw that it was proportional to the sign itself. So the delta I plus 1 minus delta I was proportional to sign I alpha. Delta 2 minus delta 1 is proportional to sine alpha. So you just add up all this, and you get the so-called a discrete analog of the so-called fundamental theorem of calculus, so which is actually given, which I give here. So a function of the difference between the function values at 2 points x2 and x1 is given by integral of the derivative of the function between these 2 points. And this df by dx we saw just now was this second order differences, and the derivative of this we saw was proportional to the sign. So this is like so yeah, I don't know how much I was able to convey to this result, but the details are actually given in my books, which you can look up later on. Among Aryabhata's very famous contribution.
If I would just like to come in, Dr. Kamble, what is more important is we all commemorated the real Indian Space Day, 19th of April, when the first Indian satellite was, Aryabhatta was uh, put in the space over there. So we all know more about calculus from a Newtonian perspective. And Aryabhatta has a limited general sway, but his work has got the seeds of calculus, is something which needs to be impressed upon, I think, for the early mathematic learners. So obviously mathematics is the, I will say, king jewel in the entire committee of sciences or learning systems. But Aryabhatta has these germs. This needs to be told and retold, and I think that is what this particular slide, this particular aspect gave it. And now to have a feel of this differential, the ratio of science in the real world discrete mathematics, I think that is beyond the scope of normative school mathematics. But yes, this is awe and reverence की जो आपने बात कही कि हिंदू ट्रेडिशन से there is an entire mathematical tradition. I think that is establishing it so very well. Lovely, lovely. Please, sorry for the interruption. Yeah, please.
Sure. Exactly, yeah. There's a continuity in the tradition, as we will also see. So one of Aryabhata's results, which I thought would be important to mention here, was his value of pi, which comes out to be 3.1416, equate to 4 decimal values, which I thought it is important because in its own right, but also because the value of pi has a great bearing on how the different trigonometric values are estimated, interpolated, and so on. So this has a great bearing on that, also on what follows in the Hindu mathematical tradition in later centuries. So this is a very interesting commentary by Neelakantha, by the Kerala mathematician Neelakantha, in his Aryabhatiya Bhashya, in his commentary to the Aryabhata, I think 15th century or so, where he says why Aryabhata uses the word asannaha, that is approaches the value of this 62,000 divided by I mean whatever, the 3.1416 thing. So it's a very nice explanation, like, which implies that pi is an irrational number. So And as we saw, Aryabhatta had given this value of the sine values for 24 different angles. And in astronomy, in navigation, it's very important to have accurate values of the trigonometric functions. So many mathematicians were very involved with improving these values, creating interpolation methods so that for arbitrary angles you will have accurate values of the trigonometric functions. Some of these steps are like Bhaskaravan's approximation from the 7th century CE, where he gives an algebraic expression for the sine function. Vateshwara's sine tables about 880 CE, where he gives, instead of 24 values, he gives it for 96 values between 0 and 90. Brahmagupta's second order formula for the interpolation formula. Then all these things, how they eventually lead on to Madhava's sine tables, infinite series, his values of pi accurate to 11 decimal places, and so on. So, the infinite series and calculus methods, how they all culminated in this is exactly the point which Raghavji was mentioning, that there is a huge continuity going all the way back to Aryabhatta, and which you can trace in Hindu mathematics. So there is a smooth transition from Aryabhatta to the calculus of the Kerala mathematicians. So here, this is just one, this is from Bhaskara one, from Mahabhaskariya. His formula for the sine function is given by this expression. And here I have shown the actual values with the circles and the approximation by this red crosses. And you can see to the naked eye, it is totally invisible. If I remember, the error was about 0.05% or so. So it's really remarkable. With this one formula, he is able to show this. So this is the sort of Sanskrit verse which, yeah.
Lovely, lovely.
Thank you. Yeah. So this was the first part of the talk, Aryabhatta. Then I would come to the second part of the talk, which discusses some facets from the Sulba Sutras. This is my cat. She's meowing. She wants some attention, really. So, yeah. So this
Tom
is the
cat after the Schrodinger's cat. I think it's Dr. Kamble's cat who is trying to come into the discourse so very well.
yeah. Usually she does not disturb me, but now that I'm having a talk, she makes it a point.
Yes, yes.
So okay. So the Sulba Sutras are actually, I decided to talk about this because I had given a course on Brihat some months back, and there I got really interested with this aspect of the Sulba Sutras, especially the historiography of the Sulba Sutras. We know, many of us know that it's so-called Pythag. Just give me one moment. I will just take her out. She's
Sure,
meowing. Sorry
sure.
about that.
So for all our other audience, we can see there is an interplay between the mathematics, the class, and the mathematical logic or mathematical knowledge is encapsulated in the Sanskrit language, and language, mathematics, and now what Dr. Kamble is going to present is its application, because the profound creation which we witnessed all across Bharat, the nook and cranny of the 32 lakh square kilometers, that's a kind of a area into which the modern republic is out there. So I think that is the manifestation of this mathematics into real architectural splendors and other creations, because that's what where mathematics gets validated. What is the practical utilization of it all? Dr. Kamble, please carry on. Yeah.
Yeah. Yeah. So. So the Sulba Sutras, I got really interested in them some time back when I knew that, of course, many of us know that so-called Pythagoras theorem is stated in the Sulba Sutras centuries before Pythagoras, and the official date of the Sulba Sutras is 800 BCE, and Pythagoras lived, I think, around 500 BCE. So there is at least a 300 years difference between them. Obviously, the question comes, how accurate is the dating of the Sulba Sutras and things like that, because yeah, there was a tendency to really post-date the Vedas and the Vedic texts from the colonial times onwards. So these are some of the aspects, and I also got really interested in the aspects of Babylonian mathematics, which was about 1700 BCE and so on. So, and I got interested with some other aspects of the Sulba Sutra, especially the one related to the square root of two. There is an expression given for the square root of two, which has some very fascinating mathematics, which I will talk about in this. And we also know some of this information on the Sulba Sutras, that they are actually texts for creating Vedic altars, the geometry of the Vedic altars, if you want different Vedic altars of the same shape but different areas, and so on and so forth. Or if you want a square alter with the sum of two other square alters and things like that. All right. So Baudhayana, Apastamba, and the Katyayana Sulba Sutras are, the most well-known Vedic text, the Sulba Sutra texts. And as I mentioned, two things I will discuss here: the so-called Pythagoras theorem and an approximation for the square root of two. So here is this famous result from the Baudhayana and the Apastamba Sulba Sutras, that which says that if you have a rectangle, the square of the diagonal area of the square of the diagonal is equal to the sum of the areas of the other two sides, which is the so-called Pythagoras theorem. So there is, in fact, no proof that Pythagoras had anything to do with this theorem, and I have written on this extensively in one of my blog articles, which I will show later. What is interesting for the purposes of our talk is one application of this this so-called Pythagoras theorem. So if you have a square of
Disconnected.
sorry. So
Please carry on. Someone.
So if you have a square of side A and another square of side B, and if you want to make another square whose area is equal to the sum of the areas of these two squares, there is a sutra given in Baudhayana Sulba Sutras, and also in the other Apastamba and Katyayana Sulba Sutras. It basically means that you take a side here B equal to the side of the smaller square, and then you construct this diagonal here, and by symmetry principles you will see that this will be also, you can construct this diagonal also, and this will form a square here, and the area of this square is equal to the area of this smaller square and this area of the bigger square. So this follows from, because the c square is equal to a square plus b square. What is this is an application, yes, but what is very interesting is that this carries an implicit proof of this result, implicit geometric proof of the result. So let us see how. So you have here one big square side A and one square of side B, and you have here this you have made this construction of side B here, and then you, as I mentioned, you make this square here, construct this square, and now let us look at the area of these two triangles, this triangle and this triangle, which I show here in red. Now you can see that from symmetry considerations, again we can see that this triangle is congruent to this one, and this triangle is congruent to this one, and so we can simply move these pieces aside from here to here, which I do here, and that will not change the area. So the area remains the same. But earlier the area was a square plus b square, and now the area is equal to c square of this. So you immediately have the fact that a square plus b square equal to c square.
Lovely, lovely. So spatial displacement kind of a proof is being shown over here.
Exactly. Exactly. Yeah. So this is a very this is a very interesting part of the sutras, and also there are also people like Datta and Singh. They have mentioned also other implicit proofs in their articles on Hindu mathematics, but this is the one which I think is one of the most striking and also one of the easiest. And even and Bhaskaracharya in the 12th century, he also gave a proof of the so-called Pythagoras theorem using similar triangles, which we are familiar with, which came in Europe only about 5 centuries later by John Wallis. And the fact that, okay, here is a list of some scholars like Konrad Müller and Datta, Amartya Kumar Datta. He is a recent one, of course, 2022. He has written some very excellent articles, Amartya Kumar Datta, on Hindu mathematics in the Bhavana magazine. So yeah, and Vibhuti Bhushan Datta has written also in 1932, has written a list of other proofs which are implied in the Sutras. So this is one aspect which I wanted to touch upon in the Sulba Sutras. And the other aspect of the Sulba Sutras I wanted to touch upon was this expression for the square root of 2 in the Sulba Sutras, which is really, really fascinating bit of mathematics, which I would like to talk about. So regarding the Sulba Sutras, the so-called Pythagoras theorem, and the historiography of the Sulba Sutras, why we don't know about the Sulba Sutras so much, and everything gets dominated by the narrative of Babylonian mathematics, Mesopotamian mathematics, and Sulba Sutras gets totally thrown out of the picture. I have discussed that in this article, the Sulba Sutras and the Pythagoras theorem, on my Substack blog. Then the things that I'm going to talk about right now, square root of 2, is the historical aspects of this is talked about in this article on my Substack blog, and the mathematical aspects in this article, the big square with the missing corner. So I'll be discussing something from aspects from this one in this one. So there is a generic method in the Sulba Sutras for finding out square roots using a geometric method. How is it done? So is by square root I mean square root of an integer number. So if you want the square root of, let's say, 5, so you take a rectangle of length 5 and length 1. So one side is 1 and one side is 5. So you can then make it into 5 squares, one after the other. And now you try to rearrange the squares so that you get a one full square. That is the basic idea behind this method, geometric method of the Sulba Sutras. So the idea will probably become clear a few steps down the line, which before I do that, I would like to show here the expression that the Sulba Sutras give for the square root of 2. It is given by this square root of 2 approximately equal to 1 plus 1 by 3 plus 1 by 3 times 4 minus 1 by 3 times 4 times 34. And they say that it is approximate, that it exceeds because of the name Savisheshaha, means that it is more exceeds the actual value of the square root. So this is an important expression why it is important, it will become clear in the few slides. So, but this is the expression that the Sulba Sutras give for the square root of 2. Here is what I was talking about. How do you, what the Sulba Sutras mean? So you have here a rectangle of side 2 and side 1. So the Sulba Sutras have not done this. This is a later day reconstruction by I think by Datta in the 1930s. So you sort of you break this square into 3 equal rectangles like this, and the third rectangle you break into further parts like this and rearrange. So A remains here, A, and B and C are taken here, B and C are taken here, D comes here, and all these other 8 strips are situated here, rearranged here. So you can see that the first, this remains. So this is not a square. This is a small corner here. That's why I said the big square with the missing corner. So there's a square here, but the area of this square, if this had not been missing, would have been equal to, yeah, the area of this rectangle, which is 2, and hence this side would have been equal to square root of 2. So you get the first approximation for the square root of 2, that is 1 plus 1 by 3 plus 1 by 3, 1 by 4, which is the first 3 terms of the Sulba Sutra expression. 1, 1 by 3, 1 by 3 times 4. This is what is given here. And and there were many attempts by scholars how the Sulba Sutra authors came up with such an accurate expression. This one is given by Thibaut, which I will not go into. I will go into the method which, because it is commonly accepted today, and it is based on this method of the Sulba Sutra for rearranging a rectangle into a square. And what is more important is that this method by Thibaut does not really give you this series kind of an expansion, whereas the method by proposed by Vibhuti Bhushan Datta and gives you this sort of a method series expansion. So this was proposed by Datta and Singh, and this was later generalized by the American mathematician David Henderson in around 2000 or so, which he published in an article in Square Roots in the Sulba Sutras, in this article. And this is the first Sulba Sutra expression. And Datta showed how the Sulba Sutra authors could have obtained this. And Henderson just simply, generalized this to higher and higher iterations to show how an infinite series can be obtained to get even more better values of square root of 2. So I think I have not shown you here how this thing is done, but that picture I don't have here, but I will just give you a very brief rundown. The idea consists in cutting off a small strip here of some width, which you have to choose appropriately, and one equal width strip from here. You choose these 2 strips and you cut them into small parts and try to fit them into this small square. That is the idea. And now you will be left with a slightly smaller side of this big square, and you will be left with here some of this area has been filled. But the thing is, after you fill this, there will still be a small square left here. Instead of this square, you will have a small square left here. So you follow this idea iteratively. Again, you cut off some small strip from here in such a way that this small square is filled. But you will see that again, it is not perfectly filled, right? And this process can be continued indefinitely, and that gives rise to this infinite series expansion, of which the first few terms were given by Henderson, and the first four terms were given by Sulba Sutras. Obviously, we don't know if the Sulba Sutra authors actually used this method or not. But the fact is that this method gives rise to this series expansion and not just to, the fractions, the final fractions. And we can see that,
So, Kamble, I
yeah.
have a small curiosity that when it all emerged initially,
Mhm.
mathematical abstractions we all champion on pen and paper, we solve the equations. That is one part of it all. But the mathematical abstraction as shown by way of the geometrical displacement. So, were our early mathematicians really working on large fields or things like that to really come up with this connecting this abstractness with the reality? Like the way you did the a square plus b square is equal to c square. So perhaps drawing a bigger square and trying to displace it across. So what was the origin of it all? Was it, I would say, was it what that real practice done on field before arriving at these equations? How it all happened? Is there some history regarding that?
Yeah, the field work is definitely there. In the Silva Sutras, you have certain astronomical methods also
Yeah.
for determining the directions, east, west, north, south. There you actually go to the field and see, you trace out the shadow of the sun and see the so-called circle method, which is given in the Katyayana Silva Sutras for finding out the directions, north, east, west, south. And obviously, a lot of it also went constructions of Vedic altars. They used bricks for their constructions and strings and bricks, the number of bricks. So all this obviously was done also on the field.
Architecture and astronomy, both the practical implementation of it gave rise to this abstractions rather
Yeah.
than okay. Mhm.
Yeah, yeah, exactly. How this geometric, physical aspect gave rise to abstractions. That's a really interesting question because this did not happen in other civilizations. In the Greek civilization, for example, they remained mostly with geometry and they did not carry out this abstraction to symbols, to numbers, to negative numbers, things like that, fractions, things like that. So this did not happen in the other civilizations. So it is really an interesting aspect why it happened in the Hindu civilization itself and not in the other civilizations. Like even the Babylonian, they were mostly focused on the geometrical aspect.
Mm.
And right. Um, yeah. So I'll just now go through, and the general result is that, when you go through all this mathematics, you can see that the square root of 2 can be expressed in this form of a series. So 1 plus 1 by x1. So x1 is 3 plus 1 by x1, x2. So that is 3 times 4. And 1 by x1, x2, x3. So these four terms is the Sulba Sutra result. Yeah.
Mhm.
But then, if you apply this method of infinitely iterating it, you get minus 1 by x1, x2, x3, x4, minus 1 by x1, x2, x3, x4, x5, and infinitely. And the first few terms are given by x1, x2, x3. And after that, the nth term is related to the n minus 1th term by this recursion relation
Mhm.
here. And if you make a table of xn, you will get 3, 4, 34, 1154, and then 133, 1714. So they start becoming really bigger and bigger. And the approximations for L, for the square root of 2 become more and more accurate. So 4 by 3 was the first approximation. 17 by 12 was the approximation given by these three terms, the first three terms. Then 577 by 408 is the Sulba Sutra approximation given by this entire, all these four terms. And then if you go to the next term, you get this fraction for the square root of 2, and then it becomes more and more accurate.
So Sulbha Sutra mathematicians, they were more interested in the practical application where we have to approximate value after certain significant digits. So
Yeah,
modern mathematics was more in approximating till infinity. That was their quest. Ours
yeah,
was more somewhere the ceiling was there into the practical implication of it all.
for sure, surely. Yeah, definitely. But there is yeah, we will see how this, some practical considerations also make it necessary for getting more and more accurate values, which we saw, for example, in the case of pi and the values of the trigonometric functions where highly accurate values were needed.
Because
So,
way with which you showed the Kodand, the Dhanush, the arc,
Yeah,
because that is something which relates, because it comes more from mathematical education, having a feel of mathematics. Like currently the textbooks are all, oh, this is arithmetic, then this is algebra, this is ratio, proportion, decimals. So linking it across in an integral fashion get somewhat difficult. But if you really come on ground, the field work, like many of the mathematical labs in the schools, they are trying to give the young learners a feel of the practical implications straight away. Otherwise, with calculators, you can all do the mathematical operations all by yourself. So
yeah,
in finite series, they need to have a lots and lots of, like, we have chemistry labs, we have physics labs, we have
yeah,
biology labs, but mathematical labs are not actually out there because people are scared by these symbols and these operations. But they have got the way you have shown how two squares converted into this. So that really gives key. If a mathematical lab work is there somehow linking, I think that abstraction goes very, very deeply, like drawing a circle in a ground. No,
hmm,
that transforms the experience altogether of a learner. I can.
absolutely. Yeah.
Great, great.
And Hindu mathematics has a lot of scope and potential for such kind of illustrations and demonstrations.
Yes, yes, yes.
Yeah. Okay. So at this point, I just want to make a digression. It is related to Subha Sutras. So there is a well-known method for approximating the value of the square root of any number. So I just illustrate that method here. So suppose we need the square root of some number n. It can in general be anything, but I take it in an integer for the present case. So
Mhm.
suppose we start with some value, test value for the square root of n, which we don't know if it is really true or not, but start with a test value. So suppose this is a test value, then at the next step, we take the new value, iterated value of the square root as half of the test value plus n by the test value. So n is the number whose square root we need to find. So this is ri plus 1. Forget about this line for it here. But in the next step, you do again for you take ri plus 2, then you replace ri with ri plus 1. You take the next step, and then you will find that this procedure brings you very fast, converges very fast to the square root of the number n. So this works because supposing the test value is more than the square root of n, then
Mhm.
uh, then it will turn out that this n by ri is less than the square root of n. So it will be always like, so you take the mean of these two numbers, and when you make them converge, they will come closer and closer to each other. So r becomes close to n by r, which means that r it becomes close to the square root of n, because if you put r equal to n by r, you get n equal to r square. So this is the well-known method, and which is been attributed to the Greek mathematician Heron. I think 200 AD or something he lived, 200 CE. I don't know. And also it has been attributed to the Babylonians. This was about 1700 BCE. So this attribution to the Babylonians was done by Otto Neugebauer in the 1920s or 1930s, and there is very little hard evidence that they actually knew this algorithm and they used this algorithm. But I have documented the research of Neugebauer in my articles, and it becomes, I mean, it's the work of Neugebauer which has in fact made this Babylonian mathematics so influential. And he was extremely biased towards the Babylonian mathematics, and there are reasons for that also, because Babylonia is has a Christian biblical significance, and so Babylonia can be absorbed into the Western narrative of the progress of civilization from the earlier baby steps of Babylonia to the modern West.
The
So
politics comes into play everywhere, even in the disciplines.
yeah, yeah. So correct. So yeah. So but this aspect I will not discuss here. I will discuss about this algorithm here. So when we do that, when we try to use this algorithm for the square root of 2, what do we get?
Mhm.
We start with an initial guess of 4 by 3, that is equal to the first two terms of the Subha Sutra.
Mhm.
1 plus 4 by 3, that is 4 by 3. And if you look at the second iteration, the formula says half of r plus 2 by r. So r is in this case 4 by 3, and 2 by r is 2 times 3 by 4. So this turns out to be equal to 17 by 12. And if you look at the first three terms of the Silva Sutras, that also equals 17 by 12. we carry this process further. We have this, the improved value of the square root of 2. We go to the next iteration, half of this plus 2 by this value, we get 577 by 408. And if you go to the next iteration of the Sulba Sutras, all the four terms, you get again 577 by 408. So this was 4 by 3, these two terms. Are you able to see my mouse also?
Yeah, we are very
Yes.
Okay. Great. So this was 4 by 3, the first iteration. Then this was 17 by 12, the next iteration. And this was the entire Sulba Sutra expression. This is the next iteration, 577 by 408. So you can guess easy enough what follows. If you go to the next iteration, you get this.
complex one, but the Sulba Sutra is a easier one to decipher and work upon.
Yeah, sure. That's true. That's true. But I just want to make this connection between this algorithm and the Sulba Sutras. So, this is a very surprising result because when you go to the next iteration, you get this number. And if you go to the next series, this is not given in the Sulba Sutras. The Sulba Sutras terminate here. But this series given by the Henderson's and Datta's method, if you extend that, you get the same kind of a thing, same value of this, and so on and so forth. That means that the two methods give equivalent results. So this is actually a very surprising result because the one is entirely geometric method and the other one is entirely like an algebraic or arithmetic method. And how can these two be the same? I will not go into the details into this, but I have written about this in the articles on my blog. And in fact,
But
and
as an expert mathematician who has delved into these abstruse concepts, what is
Mhm.
your take pertaining to the primacy of Sulba Sutras vis-a-vis primacy in terms of pragmatic applications vis-a-vis the other algebraic or other aspects? Because for a layman mindset, which is superior or which is easier? If you can delve a bit more on that.
Yeah, sure. I mean, the this algorithm which we just saw is really easy to follow. You just need a calculator, or even with pen and paper you can do so, and this gives you the same results. And this is not restrict. This you can use to any number. So obviously this method is much more general, and it is much more, you can say, useful than the Sulba Sutra methods. That's for sure. I just brought this up here because one thing is that there is this. Why should that the very fact that they give identical results is a very surprising result, is a very surprising fact. This was one aspect I wanted to bring in. The other aspect I wanted to touch upon was that Neugebauer had claimed or had the opinion that the Babylonians in 1700 BCE, they used this approximation, this method, that this was known to them. So there is this was an instance of the, like, let's say, the biases of Western mathematicians when it comes to Babylonian mathematics. This was one of the aspects which I wanted to touch upon, which I have not done in this here so much. So,
Is there some indication that this Babylonian method had
mhm.
an influence or it was inspired from the, I would say, the Sulba Sutra method somewhere or the other? Are there evidences for that? Or it was generated parallelly?
Uh, so the Babylonians, they had a base 60 kind of a system, right? So I will not go into it, of course. But the fact is that when you have some sort of a base system, it was not a decimal place value system like we understand it today. They did not have any zero or things like that, but it was a like base 60 system. So you cannot really, so you have to use sort of, some fraction, not fractions, but yeah, you have to terminate, you have to terminate. So for example, you cannot have 0.333333, for example, indefinitely. That is actually
Yes.
good 1 by 3. But you have to terminate at some point. So when
Okay.
they terminate at some point, um, they get a result, which is a number. But in the Sulba Sutras, you have the fractions, fractional values are given. So
Mm-hmm.
they have a much bigger clue of how they could have arrived at this number.
Mm-hmm. Mm-hmm.
So yeah, so these are some of the aspects which are there. I mean, it will be too much for me to go into
Perfect,
this aspect.
perfect. Perfect.
So I will
Please.
not. I will discuss about Babylonian and Sulba Sutras mathematics at the end slightly, but this was one of the things I want to talk about. And another very interesting aspect about the Sulba Sutra results is that these numbers which we saw, 17 by 12, 577 by 408, and these numbers, etc. So they have a very interesting connection to the so-called Pell's equation. So these are equations of the form nx square plus 1 is equal to y square. N is some number 2, 5. In our case, it is the number 2. And x and y are integers. So you can see that if you have, so we want to find the values of x and y, integer values of x and y, which satisfy these solutions. So you can see that, if x and y are large, so for example, like this fraction or this fraction, you can see that you can, neglect one, and you have nx square is approximately equal to y square. So n is approximately equal to square root of n is approximately equal to y by x. So
Mhm.
this so-called Pell's equation was used by Brahmagupta and others to find out approximations to square roots of numbers like n. So here we see a very practical aspect of mathematics where you need this, high accuracies and so on and so forth. And the Pell's equation was solved much earlier in India than in Europe. So sometime by the 12th century, it was perfected by the time of Bhaskara. And it was in the West, it became known for the first time in around the 17th century. Yeah, from the works of Fermat and the other mathematicians of those time. And yeah, so it could well be that they had access to the Indian texts which discuss this Chakravala algorithm for solving this. And here is what I was talking about. If you look at this equation nx square plus 1 equal to y square, you see that 17 by 12 was the first approximation. So 2 times 12 square plus 1 is 289, and this 17 square is also 289. So this satisfies the so-called Pell's equation. You go to the next approximation, 577 by 408. This also satisfies the so-called Pell's equation, and so on and so forth. So yeah, here is a brief history of the Chakravala algorithm. So there's a slight change in notation. But yeah, so there was a long history starting from the works of Brahmagupta, culminating in the works of Bhaskara too in the 12th century. And uh, and this was in the 17th century introduced in Europe for the first time by Fermat and the other mathematicians. So they sort of, they got, and interestingly, exactly the same problem which was solved by the Hindu mathematicians. One of the cases, 61, which is especially difficult, was proposed by them. So you can see this is connection between the Sulba Sutra approximation for the square root of 2 and the so-called Pell's equation. And yeah, at this point, I may also mention that these numerical algorithms for the so-called Pell's equation, the Chakravala algorithm, it is closely related also to another algorithm known as the Kuttaka method for solving linear equations, linear so-called Diophantine equations, where you need integral solutions. Like here also you need integral solutions. So yeah,
So,
exactly.
Dr. Kamble, would it be, I would say, valid with some level of approximation that the Hindu mathematics, the Hindu
Mhm.
tradition of mathematics had the germs of all the advanced mathematics which happened in the medieval times? uh, uh,
Yeah.
to some level of what kind of a statement would you, as an expert, having a comparative view of these abstruse notions and notations? Because at this modern time, maybe obviously we will be going at a much more I would say much more accurate kind of a computational methods we have evolved. But on a fundamental plane between the Hindu mathematics and the European or the Arabic mathematics, would it be true that we had the germs of it all? Question number one. And secondly, knowing that we had these germs, we had a tradition. So what kind of an extrapolation can one is obviously the national pride, the cultural pride. Oh, we had it also. Now, from 2025, 26th April onwards, okay, fine, we had this in our tradition, but what are the parallel dimensions of our tradition, which, if worked upon individually, collectively, institutionally, what areas it can project the entire domain of mathematics per se? Uh, I think I'm able to pose my two questions.
Yeah. Um, yeah, so when we think along these lines, what can it do today in today's world? One thinks implicitly in terms of what can it do, to get more achievements within the, like Western framework, that giving that as the framework. Within that framework, what can we do? I think probably it's like, important for Indians to get in touch with their own like roots of roots, spiritual philosophical roots. That is, I think, the most important, because I mean, like, there is, as you mentioned, the germs were there. Things like the so-called the binary numbers in the works of Pingala was there. The ideas of linguistics and prosody, which influenced computer science many centuries later, they were there. The ideas of calculus, series expansions, and even this, which we number theory methods we saw, Kuttaka, Chakrawala, they all were there. But it would be a mistake to go along the lines of saying that, oh, we knew it all, we were great. This chest thumping is a very pernicious fallout of this. Is not the aim of getting acquainted with your roots. I think the aim is to sort of uh, for the sake of the truth itself. The truth itself is a important enough reason, and and also to become aware of what are the differences in the thought processes between the dominant cultural narrative, which is, of course, the Western narrative, which has become the default narrative, that people don't even think that it's there can be something different. But this materialistic and mechanistic narrative of the West, compared to the so-called the holistic, or the approach of the Indian civilization, wherein you don't have this mechanistic approach, but you have this knowledge system, which the para, apara vidya, vyakta, avyakta, and to know the
One
connections
is
between.
one is you are saying that Hindu mathematics links us back to our
Yeah.
complete, our spiritual, our traditional notions,
Yes.
our motives. That is one. And on the
Yeah.
second level, you think that there is a possibility that anchored in our Hindu traditions, Hindu philosophical precepts, the approach towards solving mathematical problems, we might even come through newer breakthroughs for the future of humanity. That future you see.
Yeah,
While the
this could well be. This could well be. Yeah, this could well be.
okay.
But I think I
Let
would
me
not
come in here.
count
Yeah.
on it as the main. Yeah.
Sorry to interrupt. I would like to come in here. Uh,
Mhm.
Sir, Bhaskar sir, I would like to ask one question. You know,
Mhm.
we read when we were during our school times that Galileo, in the astronomical perspective, a lot of plagiarism which is there, uh,
Yeah.
cross to and fro from India to Galileo. I mean, the West and the India and our civilization. So in
Yeah.
astronomy, that was there. It is documented in somewhere. I'm not able to quote offhand, but so I want to I mean, as you might have researched, I'm sure of that, the mathematical literatures and our scriptures, the Sanskrit verses you've quoted so beautifully well. So just wanted to inquire that is there a continuity in the Indian mathematical texts about which illustrate a continuity, a seamless thought pattern or a knowledge format or something of that sort. Like we know we had agricultural predictions, that how much rainfall centimeters is going to happen, and this was something which an Indic farmer or our nascent raw intelligence could predict. So there again mathematics is there. And again, predicting which constellation means what, and when this constellation would arrive in the skies, and what implication it has on the human astrological charts. All this was there, this knowledge was there with us, with our civilization long long ago. I mean, this is there, which is that's how the Jyotish Shastras, and so astronomy and astrology are closely related. I have a family background of astrology, so I'm just taking the liberty and courage to say this. So I just wanted to, because when we hear from the West how they have articulated Indian progress and root of mathematics, I mean, I would not trust those sources completely, because when Galileo and Aryabhat, as far as I remember, there was some kind of skirmish, plagiarism issues. I'm not able to quote the exact point in literature. So, requested to kindly throw some light on this, because this is a dark area, gray area rather, I would say, that which is Indian and which is our civilizational ethos. And very nicely pointed out, it's a holistic narrative, which we always try to give credit to the world. We don't say that it's our thought entirely. We say let all noble thoughts come to us from all directions. But at the same time, if it's a mechanistic narrative of the West, it does not mean that the bibliography or the credit where it has to go, the root has to be pointed out. So it's a very critical question to your office, please.
Yeah. Yeah, I'll come to this Galileo point a bit later, but first I want to just mention this mechanistic narrative of the West. It's
Mm-hmm.
like in sharp contradiction to the Indian narrative. If you look at the case of like what I just mentioned, Khahara, infinity, the concepts of infinity, zero, how they are tied to like how Bhaskaras compared infinity to Vishnu, and there are quotes, verses from the Bhagavad Gita, which like there are one-to-one correspondence between what he says and the Bhagavad Gita verses, and there the idea of algebra, which in Indian mathematics is known as Avyakta Ganita or Bija Ganita. So why Bija? Why Avyakta? In fact, my book, The Imperishable Seed, comes from Bija Ganita. Arithmetic
Mm-hmm.
is called Vyakta Ganita, Vyakta, and algebra is called Avyakta Ganita. So what is Vyakta? What is Avyakta? Avyakta in Hindu philosophy is the unmanifest. Vyakta is the manifest. So the numbers are, the Vyakta forms, manifest forms of the unmanifest. And Hindu mathematicians have called algebra as the root of arithmetic, from which all arithmetic springs. So all these, so this getting aware of these roots, the connections would make us connected also to our own, thought processes, our own, thinking, Hindu thinking. And this was Srinivasa Ramanujan was in totally in tune. He was totally in touch with this Hindu thought processes, and this is very important in the present day. And coming back to the second question about Galileo, he had mentioned this, this when things are moving, like when you are on a ship, you don't know whether you're on a ship or on the water. I mean, you cannot tell. It's like the sort of the idea of relativity. If you're on the
Mm-hmm.
so if you're in a closed room totally and the ship is totally moving very smoothly, you cannot tell if the ship is moving or not. So and so this was like almost a similar statement was made by Aryabhatta, that stars, we see stars moving in the sky, but it's actually not the stars which are moving, but it's actually the Earth which is moving, rotating, because of which the stars appear to move. And Galileo was in touch with the Collegio Romano in Rome, and there in this university in Rome, the Jesuit priests, they would send all their materials from India, China, and all over the world, and they would translate the works and send it to this place. And Galileo was in close touch with them. So the works of the Kerala mathematicians from the 14th century onwards, and you see that the Jesuit priests, they come from Europe to India, and around after this around I think 15th century or so, so like about 2 centuries after the Kerala mathematics started after Madhava, and they sent their written materials, translations of Hindu texts from India to Europe. Unfortunately, we don't have any concrete evidence of mathematical texts, but there is a lot of other Hindu texts, spiritual, religious texts, which have been translated and sent there. So this aspect is there, that that European scholars of those times had access to Indian mathematics. I mean, it's a big coincidence, right? Because they were in Kerala, these Jesuit priests, they were sent here for the purpose of learning. They were trained in mathematics by Christoph Clavius from Europe and all that. So yeah. So this does that answer your question, Surbhi?
Thank you. Yes, it answers my question. Thank you.
Okay, so I know that I was a little bit technical, and if you want to go into the technical details of several of these things, the Peltz equation and the square root algorithm, you are invited to check out my article, which I have put on my GitHub repo. Bhaskar-Kamble is my name on GitHub, and Mathematical Explorations is the repo. So there you have this path you can follow, and here is the PDF article, which discusses about these things in technical detail. And I will just conclude with the importance of the Sulba Sutras, which was outlined by Abraham Seidenberg in the 1970s and 80s in two articles. So he talks about why the Sulba Sutras got pushed out of the narrative, and because there was a time till the 1920s that people did not know about Babylonian mathematics. They knew about Greek geometry and they knew about Sulba Sutras. They knew about the Sulba Sutras from the 1875, and from that time they could have made the guess that okay, the Sulba Sutras influenced Greek geometry, but no, they did not do it. They hung on with the view that Sulba Sutras were influenced by Greek geometry because they put a late date to the Sulba Sutras. And this is continued for a long time. And in the 1920s, Neugebauer started his research on the Babylonian mathematics, and then it was all taken over by Babylonian mathematics. But it's very interesting that the Seidenberg, in his articles, he makes a detailed study of the mathematics of the Greek, Babylonian, and the Sulba Sutra mathematics. And he comes to the conclusion that a common source for the Pythagorean and Vedic mathematics is to be sought either in the Vedic mathematics and Sulba Sutra mathematics, or in an older mathematics very much like it. Then he concludes, what was this older common source like? I think its mathematics was very much what we see in the Sulba Sutras. So if you look at it, read his article carefully, he says it is not the Sulba Sutras itself because of the date 800 BC assigned to the Sulba Sutras, which we know is questionable, and also because he depends on the Aryan migration or invasion theory, whatever you call it, to conclude that it was not the Sulba Sutras. But both we know are like shaky assumptions. And yeah, so obvious conclusion is that Sulba Sutras have played a much more important role in mathematics than one believes. Yeah, so I think I will just stop here. These are a few final slides on the origins of algebra and why Al-Khwarizmi is credited with it, but I will just stop here and wind up with some final thoughts that Hindu mathematical contributions have been vast and immense, and they have been nurtured by this by this metaphysical knowledge framework, which we had just been discussing a few minutes back. And it is in this backdrop that Ramanujan should be viewed, and he was closely aligned with the Hindu thoughts. And we should not view him as an outlier, and because it has the effect of pushing out the Hindu mathematical tradition from the picture. Yeah, these would be some of my final thoughts. Thank you so
I,
much.
I
Yeah.
think Dr. Kamble has really kindled, I would say, the imperishable seed, the true quintessence of the title of his book, The Imperishable Seed. Mathematics is perhaps that very seed that which carries in abstracted form the entire germs of the Bharatiya Gyan Parampara from a mathematical precept. And somewhere it just comes to me that whatever books of mathematics we have got at the elementary or various stages, if perhaps the terms and terminologies, if some of the Hindu terms can be encapsulated along with, like when arithmetic is being talked about, if the Hindu variant, the Indian variant, Hindu variant is also put around. So the philosophy, because darshan, vigyan, and vyavhar. Today, the students are largely on the skills part of it all. Oh, you get a sum without getting deep into its metaphysical, though, is a very longish thing. But we are just the skilled part of mathematics. It's something we are all ingrained into. Understanding of the strategy is one part of it all, solving a differential equation, solving a limit, integral calculus, this and that. But the fundamental philosophical precepts, what you have really propounded, presented, I think those can come if this synergy can be brought about, because human knowledge is an integral whole. And as you said very beautifully, that Ramanujan presents, he is an icon, he is a mascot of that long Hindu tradition. And your very assertion that Ramanujan knew it all, and that's why he had Namagiri. He always chanted, he had a tradition in the family. So the traditional knowledge which he inherited, and that's why at a very, very ripe age of 32, he could produce so much on the accumulated power, on the compounded power of that tradition. I think that needs to be batted over and over again. Very lovely pointers, Dr. Kamble. And I think the quintessence of it all, that this is how we can resuscitate the legacy of Ramanujan, who was the, I would say, the pole star of the Hindu mathematicians, perhaps in the modern times. And mathematics is that aspect which unravels the philosophical dimension of life per se. The practical dimensions are fine, the computational things, the algorithms, maybe the deep learning things are getting inspired from this all, the utilitarian part, but the philosophical part of it, the fundamental questions of life. I think the imperishable seed authored by you, we would really recommend through this platform and elsewhere that that needs to be taken over, because that's where young, I would say, anchored mathematician. One last curiosity, because we all talk about technology. Today, the pyramid has got inverted. We all talk about technology, engineering, but sciences also we talk about it all. But what is the current influence of Bharat, the Bharatiya Ganitagyas, in the contemporary era? We hear about the draftsman of our NEP, Dr. Manjul Bhargav, who is an exponent of mathematics himself. But Bharatiya Gyan Parampara के आधार पर where we stand in terms of the fundamental mathematicians coming from Bharat, and what are their schools of thought? What is like on technological, we have the great CEOs and all that stuff, India born ones. But in terms of mathematics, what is the current state?
Uh, I mean, I can't, I would not be the right person to answer this question. I'm not like, a total insider in the world of mathematics, and I'm not a mathematician in per se, or a researcher per se in mathematics. I'm more of a person who has investigated the connections of Hindu thought, the evolution of mathematical ideas in the Hindu civilization. And for me, what is more interesting is the connection of this evolution of mathematical thoughts with the Hindu thought,
Mhm.
and to get rid of this mistaken notion that Hindu thought is otherworldly, it is not practical, and but at the same time it is deeply connected to the to the divine, to the divinity. It does not sort of have this mechanistic approach where these divine aspects are like integrated out and become superfluous, like in the words of Laplace, for example, where he proposed that this that once you know the state of the system at some point, and if a calculator is strong enough, would be able to predict the state of the system at any point in time, so all your atoms and everything, so all your free will, etc., divinity, etc., becomes meaningless. And there is also what we are seeing these days in with the rise of deep learning, where and artificial intelligence, where everything is sort of captured by algorithms. And chat gpt, for example, it can totally sort of, one gets the impression that the human aspect, or so to speak the divine aspect, is superfluous.
Mhm.
And these are some of the most dangerous trends that are taking place in today's world, in this kind of march towards so-called technology. I mean, it is going to lead to a total annihilation of the human, annihilation of all human dignity, because the human is going to be reduced to something superfluous. And this is the direction which has to be countered, and where this Hindu thought process
Lovely.
offers and it's alternative. And it's very important to also remember that this most of this mathematics, computer science that we use today, they come from the Hindu tradition. But this Hindu tradition itself did not propagate this mechanistic approach, by no means. So these are some of the things that I am more concerned about than
Lovely,
the.
lovely, lovely. I think it was a great session in the fond memory of one of the biggest mascot. Mascots have to be icons, have to be cheered, because they encapsulate that collective wisdom, that collective spark, and perhaps sessions like these from, I would say, enthusiasts and experts like Dr. Kamble, they give us inroads into the that vast universe of explorations. And perhaps this is an ode to that mathematical चेतना. और जैसा कि डॉक्टर कामले ने कहा कि गणित और दर्शन, उनके बीच में भी एक बहुत ही अंतर्गुम्फित तत्व है, एंड ही प्रेजेंटेड अ वेरी integral view that it is a long drawn Hindu civilizational tradition, of which Ramanujan was a great mascot of. That's a takeaway we have to take along with us. Thank you so much, Dr. Kamble, for taking out your valuable time to really illumine on this, and perhaps we could have
I
more.
would like to.
Yeah, please, please, please come. If someone wants to come in, please. You can open up your camera and you can just come over. Yeah.
I can't right now open my camera.
That-
It's not working. Namaste, Kamble ji, namaste. My name is Harini. So I
Yeah.
wanted to point out something that I think, maybe the people, it's being missed somewhere, that irrational number, right? An irrational number, you are expressing and approximating to a rational number, which itself is a huge thought which was happening in 800 BC, and maybe even before that. And we are saying, is there any contribution of Indian mathematics to the modern world? The entire mathematics itself was a contribution of India. That's what I feel. So, because the very fact that you're talking about geometry and integration of geometry with algebra and with irrational numbers, that means they knew decimal number system, they knew arithmetic, they knew fractions, they knew operations on fractions, they knew about squares, exponents. So from that only the Sulba Sutras have come. So I wouldn't say that we have evolved in 16th century or something. In Aryabhata itself, he talks about the Siddhantic astronomy, which was in 4th century. But even before that, I would say 1800, you can think about this Mahasalilam, Vriddha Gargacharya. They all had astronomy, which had the mathematical aspects also. So I think we should, it is very important for us to bring that to the school education.
Thank you so much, ma'am. I would like to come in here and add another facet. कहते हैं 100 योजन मर्याद समुद्र की कूद गयो क्षण माही. This is a verse, a shloka from the in praise of Lord Hanuman. And in Hanuman Chalisa, we say that the distance between the earth and the sun can be measured through the chanting in the verses of the Hanuman Chalisa. So this is something in fact that science with scriptures, the tethering of science with scriptures is so very critical. And Indian or Hindu thought, or the civilizational Bharatiya Gyan Parampara is so deep. I would really really second Harini ji for coming in and recommend her really, and would request Kamble sir to further enlighten us on this if possible.
Harini ji had told about the importance of bringing this in the school education, and I am totally in favor. I would totally advocate this, absolutely. It just pains me that it has not been done for the last 10 years. I will not, this is something the less said, the better on this topic.
But Dr. Kamble, there are parallel efforts like Olympiads, which go on to the extent of expanding the envelope of school education.
True.
From one perspective. So are there parallel efforts like Sanskrit education? Professor Sampadanand Mishra ji has brought about an entire curriculum of functional Sanskrit. Like from grade 1, many of the schools, a Deva Bhasha curriculum he has brought about. Governments might have their own challenges. So in terms of mathematics, are you privy to certain such curriculums which can be co-opted parallelly apart from the mainstream curriculum that way, which integrates the Hindu mathematical traditions in some way or the other?
Yeah, this would require the efforts of the state for sure. We can do all we
I would like
to our to whatever extent we can, but ultimately the state is the one which is responsible after all. And what I also wanted to also mention is that what stops us from, what stops the government agencies from just making small changes in textbooks, just like when they teach about arithmetic, things like the Brahmagupta's rules for arithmetic, the negative times negative is positive, all these rules that we use today in school, they should be like attributed and sort of these small things. Yeah, sorry.
We are working on the textbooks, so that's why I was talking about. So we have included actually this whatever you talked about, Ja and all that, Rajvabhyasanam, the east-west line, perpendicular bisector,
Yeah.
All that I have included in class 6.
Yeah.
What you said about the square root of 2 from Silva Sutras, I've included it in class 8. So we are writing the textbooks with the
So
help of...
in the NCERT textbooks, yeah?
No, not NCERT textbooks. We are writing
Okay.
spares. I'm working with Professor Ramasubramanian, IIT Bombay. So
Yeah.
for Agastya Gurukulam. So we write the
Yeah.
textbooks in Sanskritam.
Yes. Yes. So that sorry, please don't misunderstand me. I'm totally, I totally appreciate and totally love the efforts that you are doing. And all of us are doing. I'm also part of it.
Everyone.
My complaint is the official policies, the state policies.
Yeah,
That's
the
my
government has to do. Sorry.
yeah, because we as individuals one can do only so much, and when the state has to play its part. But I will not use this forum to express my views on that topic.
Fair enough. I think Dr. Kamble is a man of multiple hats. He has a very fervent advocacy. His set of four lovely columns on COVID, I think we would be publishing on Rethink India as well. And that's what it comes from, the curiosity, the discovery aspect of it all. And thank you, Dr. Kamble, for really enlightening us and giving us a spectacular new dimension of mathematics, which is not just solving numericals and getting top marks in the examination. It's something way deeper, and that's where the legacy of Srinivas Ramanujan, it will be resuscitated, and that was I think over here we would be carry on in some way or the other our prayers and pranams to that noble spirit, and perhaps that tradition, once we start studying, we can have a kind of a notion back at the head of our mind that, oh, we are the inheritors of this grand spiritualized legacy of Hindu mathematics, what we are having. एंड कहते हैं ना कि ढूंढने से भगवान भी मिल जाता है, लॉस्ट ट्रेडिशंस, इफ एटलीस्ट दिस संस्कारा इज imposed upon that we had a tradition, we can nowadays a lot of references can be brought about. The imperishable seed can be a good starting point to really rekindle that lost gyan somewhere or the other. So thank you so much. Very many pranams to Dr. Kamble for really illumining us this evening. Thank you so much. Namaskar.